Very good morning to everyone. In our last class, we have seen various types of Lewis acid and along with their differentiate of mechanism also. So we concluded that AlCl3 is the most dominated Lewis acid. Now we discuss about what will happen when variation takes place in the reactants. So for that purpose, we have go for our question number 2. So here it is, question number 2. As you can see that it's also a incomplete reaction and you have to complete this one. So let's see. This is our incomplete reaction. You can see that here you have to find out the desirable products. So one is our major product and another one is our side product. Now here is benzene is there. That means you must have to do electrophilic substitution reaction. But which type of electrophilic substitution reaction? It's a Friedel-Crafts Acylation electrophilic substitution reaction, because here you can see that CH3 is there, so that means it represent the R with carbonyl group is there also. Here is carbon along with double bonded oxygen, so it's a carbonyl group is there, so obviously it's a acylation, Friedel-Crafts acylation electrophilic substitution reaction. So this part will become our electrophile at the end. Okay, fine. Now let's do it. So here is our benzene, here is our reactant, and here is our Lewis acid, that is anhydrous AlCl3. But did you see that this reactant is little bit different from all the previous one, right? And not only that, this different only, it's a bulky one. Now most of the students after seeing this type of reactant, they fully get confused because they don't know where is fusion can take place. If you see the reactant properly, here oxygen is there, oxygen atom is there, and this will be in the center of this compound, means the reactant. So it's a center atom, and there is two possibility for fusion takes place. So the first one is here. So we get one electrophile and another one is nucleophile. Okay. Now comes for the second possibility, that is here. So obviously again we get one electrophile and another one is nucleophile, like this one, right? Now you can see that in both cases, either electrophile or nucleophile, both are same, or that is equal. It will not be differentiated by changing the position of the fusion. It always be same, is it not? Okay, because this reactant is a symmetrical reactant, means whenever both sides of a center atom are equal or same, the reactant called as symmetrical reactant. Now you can choose any of the side as for prepared your generation of electrophile. So just complete all the three steps as I told in my previous lecture, and you get your desirable products. Like one is major product, that is this one phenyl ethanol, and also you get another side product, that is this one, this is acetic acid. Okay. Now how it will come in this reaction, means this acetic acid, how it will come. So for that, if you see that this one is our nucleophile, which will capture by our Lewis acid, that is AlCl3, and make a complex for intermediate state. After removal of old electrophile, that is H plus from this benzene, and this nucleophile means this old part will make a complex with this old electrophile, that is H plus. So at the end we get our electrophile as well as this side product also, that is acetic acid. Okay, understood. Now comes for question number 3. It's also an incomplete reaction. You have to complete this one. Okay, let's see. So here it is, our reaction. We have to find out our desirable products. Okay, let's do it. So here is our benzene. Here is our reactant in the presence of our Lewis acid, that is anhydrous AlCl3. Okay, fine. But there is a problem in this reactant. If you see that this one is more bulkier from the previous one, so where is fusion can take place? So here also oxygen is a central atom. This oxygen, this one is your central atom, and there is again two possibility for fusion. First one is this position, that part will be so electrophile, and remaining part, this will be our nucleophile. Okay, now comes for the second possibility. So the position is here. So this part will be our electrophile, and the remaining part, this one is will be our nucleophile. But there is a problem for this reactant. Why? In our previous one, that's a symmetrical reactant. Both sides as same electrophile can generate, but in this one it's a unsymmetrical reactant. Both sides are not equal. For this type of unsymmetrical reactant, you have to choose the less hindrance electrophile, or you can say less substituted electrophile, because that can be provide more stability to the compound, or it prepare more stable compound. So for this type of reactant, you have to choose this one as your electrophile, this one, not this one. Understood? Okay, so I have to see how much you have understood. So I explained lot of things for this one. Now you have to arrange all the things with all three different steps as I explained. So you have to find out our desirable products for this question number 3. So this is your class assignment 3. Understood? Okay. Now we continuing our topic. So next is rate of Friedel-Crafts alkylation. Okay. So for alkylation, we represent this one as a electrophile, that is R plus dash, and for acylation is this one. Along with R is a carbonyl group is there, C double bonded oxygen. So this one is for acylation. Now are supposed to be any kind of hydrocarbon like CH3 plus or maybe C₂H₅ plus, or it's go on. Clear this much? Okay. Now suppose in a reaction you have all these things along with benzene also. Now my question is, from which one we get the electrophile fast for electrophilic substitution reaction on benzene in the presence of anhydrous AlCl3, that is our Lewis acid. So you have to find the products. So that order will be our rate of Friedel-Crafts alkylation. Now if we see the leaving group tendency, that is iodine is the best leaving group so far, that will generate the electrophile first, after that bromine, then chlorine, and at the end fluorine. But rate of Friedel-Crafts alkylation not follow this leaving group tendency. So actually the rate of Friedel-Crafts alkylation is just the opposite of this one. But why? For that you have to know the mechanism as well. So for mechanism, we go for the first step, that is generation of electrophile. Assume that the reactant like CH₃Cl react with AlCl₃, and after fusion charging difference will occur, and a nucleophile captured by our Lewis acid, and finally it will separated out. We get CH3 as our electrophile and AlCl4 minus as an intermediate complex. But this step, this last one is not our rate determining step. Our rate determining step is this one, mean how fast it will donate its electron, not the separated from two compound. Now just imagine iodine. Now just imagine iodine has a large atom. It can easily maintain lots of electron with it. But in case of fluorine, it's a small in size atom, and it will not capable to hold the electrons much more longer time, and it will try to donate its electron faster to the Lewis acid. So that's why the rate of Friedel-Crafts alkylation is this one. So the size of the halogens from smaller to bigger can faster donate its electron and generate the electrophile as well. Understood? Okay. Now in case of acylation, this time is just the opposite of the alkylation process. But why? If you see that here after fusion, this part will be our electrophile, and these halogens become nucleophile. Okay, but here is carbonyl group is there, so oxygen atom having a lone pair with it. Okay, so this oxygen try to donate its lone pair to this carbon atom and fulfill its electron deficiency, because it's become electrophile. So this lone pair will be donated to this carbon atom and fulfill to its electron deficiency. So electron is fulfilled, so the generation of electrophile not be possible, so that we need bigger halogens which will able to capture more number of electrons. So one electron will captured by this halogen, again lone pair from this oxygen will donate electron to this carbon, so again electron is maintained, balance is maintained. So this halogens again try to capture this electron, means again fusion is take place. So that purpose we need bigger halogens which will able to capture more number of electrons. On that list iodine is the first, because iodine is much more bigger than other halogens. So this time it will follow the leaving group tendency from bigger molecule to smaller. So our rate of Friedel-Crafts acylation is this one, is just the opposite of our alkylation. Okay, understood? So for today's class, that is enough, and thank you everyone.